Okay, so let's talk about where the trig functions are continuous. Or not continuous, just what values are in their domain. We started talking about that in class today. So let C be a real number in the domain of the given trig function. So we started saying that the domain for each of these, so sine and cosine, there's no discontinuities there, no spots where the function is interrupted. And so sine is all real numbers and cosine is all real numbers. That's where the easy part ends. And now we have to be careful because tangent and cotangent, secant and cosecant all have limitations to their domains or restrictions in their domain. So these are the good ones. All right, so if we've got, I think we started by talking about cosecant. Just because that is the reciprocal of sine. So we said cosecant is going to be fine everywhere except where sine is 0. Because again, remember this is 1 over sine. So anytime we flip over a 0 that would occur at a sine, we're going to have a problem with cosecant. And so what we talked about in class today was that it's going to be, the problem spots are going to be at plus or minus n pi or pi n. Let's go with n pi. And we said n is an element of the integers. And again, that funny looking z there stands for the integers. So these are the problem spots. All right. So as long as you're not choosing one of those, an integer multiple of pi, then you are in good shape. In fact, we probably don't need that pi, the plus or minus, since I indicated that it's an integer. So just any integer times pi is going to be a problem spot. And so we would say the domain is everything but this. Okay, then for secant of x, this is the reciprocal of cosine. So secant is going to have problems everywhere where cosine is 0. So if we think about what cosine looks like, it starts up here at 1, and then it goes down, and it comes back up, and it's going to keep going like this forever. So again, this is 2 pi right here. And so we would say, oh, I see that this is going to be a problem here, and this is going to be a problem here. This is pi right in the center. So 0, pi, 2 pi. That means these happen at the half pi. So this is pi over 2. This is 3 pi over 2. This is going to be 5 pi over 2. 7 pi over 2. All right, so we think about how could we say that, because it's not every integer multiple of pi over 2 like it was here for every integer multiple of pi. Here it's just the odd pi over 2's. And so we could say that the problem spots for this are going to be at n pi over 2, where n is an odd integer. All right, so that's the problem spots for this. That is one way that you can write it. I would say as long as you specify that it's an odd integer, that's probably the easiest way to write it. The other way you could write it, I don't know that this is really necessary, but you could say that it's pi over 2. Let's start at pi over 2 because we know that's our first spot where we have a problem, and then just add integer multiples of pi to it. And again, n is an integer. So that would be another way to write it. So if you can remember that n has to be odd, that's probably the shorter way to write it. But if you can't, just say that start at pi over 2 and then increase by integer multiples of pi. Okay, after that, the other two are not going to be any different because remember, tangent is just sine over cosine. Boy, this is really smushy. How about I write it in here? Tangent is sine over cosine. So tangent is going to have the same problem spots as secant would, because that is where we end up with a cosine in the denominator. So this is going to follow the rules for secant, or follow the secant domain. And then cotangent is cosine over sine. And so this is going to follow the cosecant because it's also going to have a sine in the denominator there. So this is follow cosecant domain. All right, sorry, this is so smushed. Okay, so we just read the intro part here. Let C be a real number in the domain of the given trig function. All right, so what we're doing here is we're listing all the problem spots. This has none, the domain is all real numbers. This has problem spots at integer multiples of pi. Same with this, cotangent has problems with integer multiples of pi. And then this has problems at n pi over 2, where n is odd, an odd integer, and tangent is going to be in the same boat. So it's saying as long as you avoid those spots for those functions, then again we can do the same thing that we've been doing. Sine is behaving very well everywhere, and so we can just plug in. Cosine is oops, this should be a C. I don't know how that slipped by me. Cosine behaves well, so we can just plug in that value of C. And again, here it's saying as long as C is not a trouble spot, just plug it in. As long as C is not a trouble spot for cotangent, just plug it in. Same thing with here. All right, so again, we've gone through just your base, single x's to powers, and then we've moved up to polynomials, then rational functions, then radical functions with a composition so that you can have more than just an x under there, and now we've got trig functions under our belt too. Okay, so we'll know what to do with those. So let's practice a couple of these. So our first example in here, part A in example 5, is it wants us to find the limit as x approaches 0 of tangent of x, and we say, well, is 0 a problem spot for tangent? And then we look and we say, well, tangent is following the rule for secant. And so that only spot is if I end up with an odd multiple of pi over 2. And that is not what 0 is. 0 is even, so if I put in, I just, no matter what, this is not an odd multiple of pi over 2, because if I put in 0 here, I get 0, which is not an odd multiple of pi over 2. So this is going to be fine. So then it's just asking us to do tangent of 0. All right, so then what is tangent of 0? And this would be a great time to just kind of revisit your unit circle. But at that point it is 0 because it's sine. So sine at 0 is 0 over cosine. Cosine at 0 is 1, so it's just 0. Again, if you have forgotten these things, make sure you print out a unit circle and fill that in. Okay, in this one, we've got the limit of x times cosine x as x approaches pi. Again, there's a multiply in here, so this is two functions multiplied together. All right, so we're just going to evaluate, plug stuff in, because again, cosine has no limitations at all. It's defined everywhere in the real numbers. So we'll put pi in there. So in this place, for x, we'll put in pi times cosine of pi. All right, so that pi is going to stay there. All right, so then cosine of pi. Hopefully you remember, since that is over here, and that coordinate is -1, 0, that this value is -1, and so we end up with negative pi. Okay, and then the last one. All right, I'm going to write this a little bit differently. I'm going to write this because, again, remember that this means the same thing as this. All right, which we learned on a previous page, that if we're taking the limit of this, then we can write it as the limit of sine x as x approaches 0, and then just square whatever we get. Okay, so when we do that, then we would just evaluate this by plugging in 0. So sine of 0, again, unit circle here. This is the point 1, 0. And since sine is the y coordinate, it's going to be 0. So it's just 0 is what the inside value is, and then it's telling us to square it. Either way, we end up with 0. Okay, again, we'll practice more of these, but hopefully that kind of goes along with what we're saying. Really, they did not address any problem spots, so we will have to talk about that. But these are the more straightforward ones where the X value they give us is not a problem spot. All right, but again, we will talk about problem spots. Okay, so strategy for finding limits. So we have been very fortunate in all the ones that they've given us in that we are allowed to plug the X value or the C value in that they give us. But reality is that that's not always going to happen. And so we have to have other strategies for finding the limit when it does not allow us to plug it in. All right. So here's what we're going to say, and then there will be sub-strategies that we'll use with this. So let C, again, this is our X value, let C be a real number, and let f of x and g of x be two functions that are equal for all C values or all X values except at C. All right, so these two functions agree everywhere except at this point in question. And then they don't agree. And in an open interval surrounding C. All right, so it's got to match everywhere in an open interval containing C, but not necessarily at C. All right, and we'll draw a picture of this in just a second. If the limit of g of x as x approaches C does exist, then the limit of f of x also exists, and those two limits are the same. All right, now I'm going to draw a picture that's going to go with the next example that we do, and I'm drawing this because it's one that we've already seen and done. And that was the very first problem we did in section 1.2 notes, which was the x cubed minus 1 over x minus 1. If you remember that, we factored it out and canceled. So the original function looked like this. I can't remember where its vertex was. It was somewhere over here. I think it was at -1/2. So it came down like this. And then at the point 1, so if this is a half and this is 1, then 1's about here. At the point 1, we had a hollow dot because it was not defined here. I think this was 3, if I'm remembering correctly. All right, and again, this was our original function, f of x. But then what we did was we simplified this and came up with a second function, g of x, that did not have that problem at 1 because we canceled it out. We ended up with g of x equaled x squared plus x plus 1. Right, and what g of x looked like, again, I believe the vertex was here at -1/2. What it looked like here was there was no hollow dot. It just went along like that. All right, and here it was defined to be 3. We don't need that dot there, but I just want to contrast that was a hollow dot not included there, and that this was a solid dot because it was. So here's a type of example that we can look at. We will revisit it in just a second, but it's saying if I can find two functions that are exactly the same everywhere in an interval around our C, right here, except at C, I can't do direct substitution in here. If I'm trying to find the limit as x approaches 1, I can't plug it in because it's going to make 0 in the denominator. But this guy, who behaves exactly the same everywhere except at that problem spot, which is not a problem spot for that, if I were to take the limit as x approaches 1, I would get 3. And so what it's saying is since they're identical everywhere except at that one point, I know that the limit of this, the troublemaker, is going to be the same as this, the one that has no problem. All right? So our strategy for each of these, and again, it will be different depending on the type of function we have, but our strategy for all of these functions that we come to where there is some value that poses a problem and we can't just do direct substitution, we're always going to look for a second function that is nicely behaved in that spot, and we can find the limit of that and say, oh, that's what the limit is there too. All right? Hope that gives you a big picture. All right, so let's look at the next example, example 6 at the top of the next page. And this is exactly the example I was just talking about. All right. And if you remember, when we did this, we did do a graph. So remember, our 3 strategies are finding the limit graphically. So we did draw a graph of that, and we saw the exact picture that we just drew. The second way was numerically, and if you remember, if you look back, we have that table of values, and so we saw that yes, as x was getting closer and closer to 1 from both values less than 1 and values greater than 1, it was approaching the value of 3. And so now we're going to show this analytically. All right, and again, analytically is the way that we would like to do it. All right, so if I take f of x, and again, my first strategy is find that g. All right, this is my big picture. What is that function that's going to behave like this everywhere except at that point 1? So if you remember, we took this x cubed minus 1 over x minus 1, and we said, hey, I remember how to factor this because it's a difference of cubes, and it factors into x minus 1 times x squared plus x plus 1 over x minus 1. All right, then we said, oh, these cancel, and I've got some new function, x squared plus x plus 1, which I'm going to call g of x, and this is the function that's going to behave exactly the same everywhere except at that problem spot. All right, so we're going to say let g of x equal x squared plus x plus 1 for all x. All right, so then we can say for x not equal to 1. All right, so then we can say for all x not equal to 1, f is identical to g. All right, they behave exactly the same way. Again, we look at this picture back here and say, yep, they're the same except at that one spot. Okay, so then because the limit as x approaches 1 of g of x exists, all right, pause for a second. How would we know that the limit of that exists? Well, if you remember, we said any polynomial, the limit exists because we can just plug the value in. So if we were to try and find the limit as x approaches 1 of this function, because it's just a polynomial, we plug it in. So we would plug in 1 squared is 1, plus 1 is 2, plus 1 is 3. All right, so because the limit as x approaches 1 of g of x exists, we can apply theorem 1.7, the one that we just did on that last page, theorem 1.7. And so then we can say that the limit of f of x as x approaches 1 is the same thing as the limit as x approaches 1 of g of x, and that equals 3. All right, so then the limit of f of x equals the limit of g of x, which is 3. All right, and again, I'm just going to plug this in case you want to see that. We just plug in, we get 1 squared plus 1 plus 1, and that gives us the 3. All right, so first strategy that we're going to do is just see if we can factor and cancel. All right, so that would be 1, factor and cancel. Okay, so before we do all the techniques that we're going to do, this is just kind of like a sneak peek, but it's going to say, let's look at some strategies that we can do. So 1, learn to recognize which limits can be evaluated by direct substitution. So those, again, those are the ones that I keep going through, and we would say, all right, any x, any power of x, any polynomial, any rational function, as long as the denominator is not 0, any radical function, as long as we don't put anything under an even index that's going to be negative under there. And then we've also talked about some trig functions. So as long as you're not putting in anything that's going to make the trig function undefined. So any of those, which is quite a sizable set, then we can just do them by direct substitution. So always our strategy is just plug it in, see what happens, and hope for the best. Okay, so then if direct substitution doesn't work, as in the case up here. If direct substitution doesn't work, then our next strategy is to try to find that function g. So if the limit of f of x as x approaches c cannot be evaluated by direct substitution, try to find that function g that agrees with f for every x other than c. All right, and then choose g so that the limit of g of x can be evaluated using direct substitution. So right now we have one strategy, factor and cancel. We're going to come up with two others to find that. So we're going to just make sure that we can plug in. Once we do that, then we're going to apply theorem 1.7 again, which says that if I have two functions, f and g, that behave exactly the same everywhere except at that one point, I'm going to take, and the problem point is here when we try to take the limit of f, I'm going to do direct substitution with this one and then conclude that the limit of this is the same as the limit of this one. All right, you could also use a table or a graph to reinforce your conclusion. Use your graphing calculator. We're not saying that you have to graph the function. Just you could let your calculator make a graph for you. Okay, so again, we'll do another one just like example 6 up top there, and we're going to divide out. All right, so first thing it says to do is, again, I would always try direct substitution first. Just if it works, then great, you're done. All right, so we would try and do a direct substitution, but as soon as I plug in -3 down here, I see that we have a problem because this ends up being 0. All right, so direct substitution fails. Because we get 0 in the denominator. All right, in fact, I want to do it in the numerator too, just because I want you to see what happens, because we're going to talk about this specific instance in just a second. So if I plug in -3 up top, so I get -3 squared plus -3 minus 6. -3 squared is 9. Plus a -3, and then minus 6. We also get 0 in the numerator. So what we end up with is, by direct substitution, we end up with 0 over 0. In just a second, we're going to talk about what that means when you get 0 over 0. That actually is a very hopeful thing, that we can find that function g. There are other situations where I might have like 3 over 0, and this would be, this is problematic. This is not fixable. We could not find a g that works, but in this case, we can find a g that works. Okay, so then let's try doing the dividing out or factoring technique. So we're going to say, all right, if I take x squared plus x minus 6, sorry, that might have been cut off. If I take x squared plus x minus 6 over x plus 3, and I'm going to factor the numerator, and then I've got this. All right, again, that 0 over 0 is indicative that they share a common 0, or in this case, they share a common factor. So we probably should end up getting x plus 3 as one of the factors, and then in fact, x minus 2 will be the other one. All right, then we can cancel out, and then we would end up with x minus 2. And this right here is what we're going to choose as g of x. So let g of x equals x minus 2. All right, so at everywhere except -3, this function f of x is exactly the same as g of x, right? And so we would say, cool, that's exactly what theorem 1.7 asks us to do, or is to find that function g of x. All right, so as long as x is not -3, g of x and f of x are identical. But again, g of x is defined at -3, and therefore we can use theorem 1.7. And we'll say, okay, well then the limit as x approaches -3 of f of x is going to be the same as the limit as x approaches negative 3 of g of x. And this I can do by direct substitution because I have no problems right here, right? And so we end up getting negative 3 minus 2, which is negative 5. And therefore we can conclude that the limit of this, our original function, is negative 5. All right, hope that's good. Okay, let's take a look at the next page. So again, I said I wanted to point out specifically that idea of 0 over 0. So in exercise 7, direct substitution produced the meaningless fractional form 0 over 0. Again, you can never divide by 0. So this is not defined, but people sometimes say, well, 0 over 0, since the numerator and denominator are the same, shouldn't that be 1? No, it's not. It's just, it's weird. So an expression such as 0 over 0 is called an indeterminate form. All right, an indeterminate form, because you cannot, from that form alone, determine the limit. All right, so we will find other indeterminate forms. Infinity over infinity is another one, but for right now, we're just going to look at 0 over 0. Okay. So, as I mentioned, there are going to be several techniques to find that g of x. If we look at this one right here, we see that actually I can't factor this. We don't really have any factoring techniques for when there is a square root involved in the function that we're talking about. So this is going to be our second technique. We're going to number this as 2. So the first one is factor and cancel. The second one is we're going to try to rationalize the numerator, not the denominator. All right. So again, let's just try direct substitution. We're always hopeful and optimistic that that's going to work. So if I plug 0 in for x, I get 0 plus 1 is 1. Square root of 1 is 1. 1 minus 1 is 0. So in the top, this gives us 0. And then I do direct substitution into the bottom, and I also get 0. So again, we have that indeterminate form 0 over 0. So I need to find that function g of x that's going to behave exactly the same way as this function everywhere except at 0. All right? So again, note that the limit as x approaches 0 of the top is equal to 0, and the limit as x approaches 0 of the bottom is 0. So we can't do direct substitution. Okay, so we're going to find g by rationalizing the numerator. And again, most often we say rationalize the denominator, rationalize the denominator. So it's a little bit weird that we're asked to rationalize the numerator. And most often that is what we will be doing in these problems. On occasion we might see a rationalize the denominator, but for the most part it's going to ask us to rationalize the numerator. All right, so what the heck does that mean? So let's take f of x, which is the square root of x plus 1 minus 1 over x. And so when we rationalize the numerator, it means that we're going to multiply it by its conjugate. All right, so we end up with square root of x plus 1 plus 1. And then we do the same thing to the denominator. Square root of x plus 1 plus 1. Now, my guess is your temptation is going to be to distribute this to the denominator, but hold off, because again, this guy is the problem. That's why we are getting, that's why we can't just do direct substitution, because I got 0 in the bottom. So my hope is that I'm going to have something that's going to happen at the top that's going to let me cancel that out, because while he's in the bottom like this, we're always going to have that problem. So I want him to be ready to be canceled out and be factored out. If he's distributed through to this, I might not notice it as easily. So just leave that guy, the problem guy, right there. All right, so then let's distribute and do stuff to the numerator, and we're just going to leave this denominator just as we have it. X times the square root of x plus 1 plus 1. All right, in the numerator, we should get x plus 1. All right, so the firsts, and then we're going to get plus square root of x plus 1, and then we'll get minus square root of x plus 1, and then we just end up with minus 1. Again, you don't need to write this step because they're always going to end up canceling out. So let's just knock them out, and we end up getting the x plus 1 minus 1, which just leaves us with an x in the numerator and an x in the denominator, which we're happy about because those we see will cancel. All right, so now I can cancel them out, and I end up with the function 1 over square root of x plus 1 plus 1. And this is what I'm going to choose as my g of x. Because again, this, just by multiplying it by this very fancy form of 1, doesn't change the value of the function. It just changes the appearance of the function. And so then goes along, these two are equal. This is equal everywhere except at that value we crossed out, which is going to be a problem at 0. And so this remaining function is exactly the same as f of x, except not when x is 0. All right, at x equals 0, these two are not equal to each other. So these two are equal except at x equals 0. All right, so now we say, okay, now I have my function g of x that behaves like f of x. So now apply theorem 1.7, and it says that the limit as x approaches 0 of my original function, f of x, which is square root of x plus 1 minus 1 over x, is the same as the limit as x approaches 0 of my new function g, which is 1 over square root of x plus 1 plus 1. And then I'm just going to do direct substitution. So here I'll end up with 1 over, I plug 0 in there, and I get 0 plus 1 is 1. So this ends up being square root of 1 plus 1, which ends up being 1/2. All right, so the limit of this is the same as the limit of this, which is 1/2. All right, so let me just draw what this looks like for you. So at 0, it is 1/2. So again, this is my function f. So it's undefined there, but we're saying that it should be 1/2. And then at -1, it's 1. And then it comes down a little bit here. At +1, it would be around right here. All right, so it looks something like this. Notice the function is not defined to the left of -1, because then I would end up with a negative under the radical. All right, so this is the graph of f of x. And so we can see from this that as we approach values from the left of 0, we end up at 1/2, and from the right of 0, we end up at 1/2, even though the graph is not defined there. All right, I'm going to ask you to fill in this table on your own. All right, so again, you're going to enter this into your calculator, and I would suggest doing, as you type that in to your y1 or whatever, you're going to type in, you need a parentheses around the numerator. All right, then you're going to hit your square root key, and it's automatically going to open a parentheses for you. And then you'll type in x plus 1 and make sure you close that parentheses. And then -1. All right, so this is the parentheses for the radical. And then we need to close the parentheses for the numerator and then divide by x. Right, and then second trace to get to the calc function. And then you can just start plugging in the values. If you end up with an error, oh, and then you're going to do 1 for value. If you end up getting an error when you try to do this, it means that your window is not containing these numbers. So just make sure you check your window to make sure that, like, maybe set it for your X min to be, I don't know, -2, and your X max to be +2. And then just based on what we see here, if you do your Y min, your Y min to be -2 and your Y max to be +2. All right, so try that. If you end up with an error, go change your window. All right. Okay, we have this very interesting theorem that comes up here, which doesn't seem like it should be super useful, but we will use it a couple times. Again, I tell people that my husband is a gadget guy, and he likes to buy me gadgets because he would want to get the gadget. And so we have a whole drawer full of stuff in the kitchen that I don't use. Something that peels a potato and makes spirals out of it, and all sorts of fun things. This is one of those theorems where we think, when am I ever going to use it? And it's just going to sit in a drawer for a while and we won't use it. But there will be a couple occasions where we're going to pull it out and it's going to really save us. So anyway, this is for special cases where we just cannot do one of these techniques. All right, so it says, so I've got this function f of x right here. All right, I also have these two functions h of x and g of x. And h of x is always less than or equal to f of x, and g of x is always greater than or equal to f of x. All right, so imagine that we've got something like this. I don't know, I've got some function f that does, I don't know what, maybe that, right? And then I've got some function h of x that's always underneath f of x, it's always less than it. And I've got some function g of x that's always above it. Let me put this a little bit closer to it so that it kind of touches it at this point. And let me do it so that that touch point is not necessarily 0. So let me say that h of x is always below f of x. So this is h of x, and this is f of x. And then g of x is always above it. All right. All right. So we've got this situation right here where f is trapped in between g above it and h below it, right? And so that's true for all x except in an open interval containing c, except possibly at c itself, right? So again, maybe f is not defined there or something like that, all right? And if the limit as x approaches c of h of x is L, and also the limit of g of x as x approaches c is L, then the limit of f exists and it's equal to L. All right, so the reason it's called squeeze theorem is because g and h are both having its limit at this same point right here. And we'll call that point L. All right, so h is coming up and it's hitting L and it's squeezing, or it's always down here somewhere. And g of x is reaching that same point. And f is trapped in between them. So they're saying if f is trapped in between them and these both approach L at this point C, then f has no choice. It's squeezed in between there. It can't get out. So its limit also has to be L. All right, so again, the reason they're introducing it now is because they need it to prove these two things. We're not going to prove them. If you would like to read the proof, you can. We're not going to prove them. We're just going to state them. That here are two special trig limits. Again, we would like to plug 0 in here and do direct substitution. But if we do that, we end up with sine of x is 0 and x is 0. And so we've got that indeterminate form again, but it's saying if they use the squeeze theorem, which they do in the proof, they can prove that it ends up being 1 as the limit. All right, and so this is just something I would memorize. Again, I don't know that, I mean, we can't factor, we can't rationalize, we're just gonna have to trust that this is true. All right, and then the second one is if I've got 1 minus cosine x over cosine x, and I'm taking the limit of that as x approaches 0. Again, if I try plugging in 0, I get 0 in the denominator. Oops. If I plug in 0 here, I get 1. So it's 1 minus 1, which again goes to 0. I have that indeterminate form. So there's not a technique that we can use other than squeeze theorem to show that this ends up going to 0. So you're just going to have to trust that this is also true. Again, if you would like to see the proof, you can look at that in the textbook. Okay, last page here. All right, so now they're going to give us ones. Obviously, they're not going to give us the easy ones of this. Limit as x approaches 0 is 1. They're not going to give us that. That would be too easy. They're not going to give us this as x approaches 0 of 1 minus cosine x of 0. Whoops, not 0. Over x is 0. They're not going to give us that. They're going to give us things and make us think how we can apply these two. All right, so tangent, darn, that's not one of them that we have. All right, so let's just think about what we can do. So we can say, well, I know that tangent is sine over cosine. So first of all, let me write this x right here as 1 over x. And then I'm going to write tangent as sine x over cosine x. All right, so again, I'm looking at this as like 1 times tangent, and then I'm just unmultiplying them. So I get 1 over x, and then my tangent I'm turning into sine and cosine. Sine over cosine. All right, and again, these are all the trig functions I know if I can't use direct substitution. These are the ones that they're telling me exist. All right, so then I would say, all right, I got to find some way to make it look like one of those. And I can see that I have that sine x in the numerator and I have an x in the denominator. So now I'm just going to shuffle these. So I switch the numerators here, and I'm going to rewrite this as limit as x approaches 0 of sine x over x times 1 over cosine x. All right, now I'm going to remind you that one of the very first things that we talked about in this section was that if I have a product of two things, and I'm taking the limit, that I can take the limit of the first times the limit of the second. All right, so this is going to be the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine of x. All right, so now according to theorem 1.9, this is just 1. And then according to direct substitution, if I plug 0 in here, cosine of 0 is 1, and so I end up with another 1, and so this gives me 1. All right. Okay. Let's try one more. So find the limit as x approaches 0 of sine 4x over x. All right. You might think, well, dang, that's so close, but it's not what I want. All right. Again, when they say this, sine x over x, that the limit of that as x approaches 0, x is just a random variable in here. We could put sine of theta over theta and change that to as theta approaches 0. We could put limit as w approaches 0, sine of w over w. There's no reason it has to be x. As long as the numerator, the argument of the sine and the denominator are the same, this is still going to be 1. All right? So really what we need in this case is limit as x approaches 0 of sine 4x over 4x. Right? They match, and so this would be 1. So we need to find a way to make sure that this denominator also has a 4 in it so that we can apply this. Right? So I would like to just put 1 in there. So I'm going to say limit as x approaches 0 of sine 4x over 4x. Well, you could say, Mrs. Taylor, that is not legal to do. You're right, it's not. I can't just put a 4 in there. But I can balance it out by putting a 4 up top. And then these could cancel, and I'd get right back to this. But what I'm doing is I'm adding that extra very fancy 1 so that this now is in the form of this. All right? Now this just becomes a scalar times that. So I can pull this 4 out front by our scalar rule and say that the limit of this is 4 times the limit as x approaches 0 of sine 4x over 4x. This is now 1 by theorem 1.9, and that's 4, so this becomes 4 times 1, and we get 4. Okay, we'll talk about all of this in class next week. Bye.